Here, we're going to prove this statement by proof by induction. This one's a little bit different to some of the other ones we've seen because it's an inequality, not an equality. We're going to see how we can still use proof by induction in this case. So, as always, start with step 1, which in this case, we're going for n is greater than or equal to 2, so it's when n is equal to 2 is our base case. So the left-hand side is 2 times 2 factorial, which is 4 factorial, which is 24. The right-hand side is 2 to the power of 2 times 2 factorial squared, which is 4 times by 4, which is 16. And 24 is indeed bigger than 16. Therefore, the base case holds for n equals 2, because this one is bigger than this one in that case. Step 2 is when n is equal to k, is our assumption. So we're going to assume that 2k factorial is bigger than 2 to the k times k factorial squared. Step 3, our inductive step when n is equal to k plus 1. What we want to show is that 2 lots of k plus 1 factorial is bigger than 2 to the k plus 1 times k plus 1 factorial, and then that factorial squared. So this is what we're trying to show in this case. And we're going to have to use, obviously, our assumption like we always do. So starting with the left-hand side, let's simplify that a little bit. That's 2k plus 2 factorial. And I'm going to split that up into 2k plus 2 times 2k plus 1 times 2k factorial by breaking up our factorial and pulling it apart a little bit. And what I'm going to notice is that this 2k factorial is part of my assumption. So what I know is this thing is definitely bigger than 2k plus 2 times 2k plus 1 times 2 to the k times k factorial squared. Notice these are not equal. This one is bigger than this one. So we don't have an equality going all the way through this. We have an inequality, but we now know that this left-hand side is bigger than this. Okay, what can we do now? Well, I'm now going to use a little bit of equality. I'm actually going to factorize out a 2 from this one. This is 2k plus 1. This is 2k plus 1. And then these bits are still the same. Now, the 2 times by the 2 is going to give me, sorry, the 2 times the 2 to the k is going to give me the 2 to the k plus 1, which is what I want in my final answer, so that's good. And then I've got a k plus 1, and I'm going to take this k factorial, k factorial squared, sorry, I've got k factorial times k factorial. I'm going to write one of them here, and then I'm going to write 2k plus 1, and I'm going to write the other k factorial here. I've still got the k factorial squared. I've just split them into 2 separate bits of the product here. Now this one here, I can simplify into k plus 1 factorial, k plus 1 times k factorial. But then I've got 2k plus 1 times k factorial left over. Now what I want is to have another k plus 1 factorial. But this doesn't give me k plus 1 factorial because this isn't k plus 1. So what can I do here? Well, the trick here is that this is an inequality. It is not an equality. So I don't have to find something this is equal to. As long as this is bigger than the next step, that's fine. And what I know is this is definitely bigger than, keeping all of that first bit the same, this is definitely going to be bigger than if I make this k plus 1. Because given that k is an integer bigger than 2, 2k plus 1 is definitely bigger than k plus 1. So this line is definitely bigger than this line. But now this we can simplify into 2k plus 1, k plus 1 factorial, and then here I've got k plus 1 factorial, which is 2 to the k plus 1, k plus 1 factorial squared, which was my right-hand side. So here I have shown that the left-hand side is greater than, I've used the greater than at 2 stages, but that's fine, greater than this one. At no point did this go less than, it only ever went greater than. So this is definitely bigger than this. And that just leaves us to do our last step, which is our conclusion. And this is the same as always. So our conclusion says that hence by mathematical induction, as it is true for, in this case, n equals 2, and if it is true for n equals k, it is also true for n equals k plus 1. Oh, just popped off the edge of the screen there. There we go. It is true for all integers greater than or equal to 2. And we finish our proof by induction. Now notice the slight adaptation we had to make for this inequality one. It's quite a nice little way to do it, a little bit different to the other ones we've seen, but it does still hold and does still follow the structure of a proof by induction.